So in terms of the electrostatics, the electrostatics is actually a chapter for grade 11s and grade 10s that we take on to metric. So, but this electrostatics is very much dependent on grade 10 work more than it is on grade 11. So in terms of the electrostatics, there are some things that we need to cover from the previous grades that are very important, right? The first important aspect that we need to look at is the definition of a charge. So what is actually a charge? Before that, what is actually electrostatics? Electrostatics is a breakdown or is a makeup of two words, and then the first word is electricity, the second word is statics. And then so here we know we are talking of flow of charge, and then here we know that we are talking of rest. And then in most cases, when I want to simplify the concept of electrostatics, I normally say electrostatics is electricity at rest. So in this case, when we talk of electricity at rest, we will be discussing on what we call a charge. So what is actually a charge, guys? A charge is defined as or is a physical property of matter that causes it to experience a force when kept in electromagnetic field. So whenever we are discussing on a charge, you must understand that we have what we call an atom, and then an atom is a basic unit of matter, and then it contains charges. So these charges are protons and electrons. So in terms of this charge, there will be protons and also there will be electrons. And then according to these things, we know that protons are what they are positively charged, and then electrons are negatively charged. So we already understood the concept of electrons. So electrons are the ones which are removed and transferred to to other objects. So protons always remain within a surface of a material, and electrons are the ones that have energy, and then they are the ones that move about different types of material. They can be transferred. That's why we always talk about the principle or the law of conservation of charge. We say that in an isolated system, the charge remains constant. So in this case, it means that in terms of the charge, if we bring two charges together and then we separate them, then what we know is that those two charges will transfer equal amount of charges amongst themselves, and that phenomenon is actually called the quantization of charge. So a charge is quantitized same as light, and then the word quantitized means the charge is found in pockets of eggs and solid in dozens. So we can talk about cold drinks in crates, etc. So all charges are the multiples of a smaller charge, right? So in this regard, let us give a brief example before I go further. Let us assume that you have three metal spheres. So the one metal sphere carries approximately -2 times 10 to the -11 coulomb, and then the second sphere carries approximately let's say 5 times 10 to the -11 as well. This is supposed to be a 5. Okay, and then the third sphere carries approximately -8 times 10 to the -11 coulomb. And then we said to you, these spheres are brought into contact and then separated, and then we want to know what is going to be the charge on each sphere. So these are three different spheres, so they undergo separation of charge. And then how do these undergo separation of charge? In this instance, we have Q net that can equal to Q1 plus Q2 plus Q3, and then divided by 3 according to this formula. And then now we bring those spheres together and then we separate them. So the first sphere, I said to you, had -2 times 10 to the -11 coulomb, and then the secondary sphere had 5 times 10 to the -11 coulomb, and the third sphere had approximately -8 times 10 to the -11 coulomb. And then I'm gonna take all of these things and divide them by the number of spheres, which is 3. And then whenever I do my calculations, I end up having negative 1,67 times 10 to the -11 coulomb. And this will be the final charge separation. So each sphere will now have this amount of charge, which is -1,67 times 10 to the -11. So in terms of the quantitization of charge, so we know that the charge of one electron, it will consist of charge of an electron, which is 1,6 times 10 to the exponent -19 coulomb. So this is to say that each charge will consist of the number of electrons multiplied by the charge of one electron, and then this is normally called QE. So if I'm looking for a charge on sphere 1 and they give me number of electrons, so I'm going to use this formula where N will represent the number of electrons, Q will represent the charge of an electron. And the charge of an electron is always 1,6 times 10 to the exponent -19. So the charge of an electron, remember I said electrons are negative. So in this case, it means that for charge of an electron, I'm gonna put a negative. So when they want the charge of a proton, then I'm gonna use or a positively charged sphere, then I'm gonna use a positive 1,6 times 10 to the exponent negative 6. And then the secondary thing that we have is the how do we calculate the transfer? Okay, let's try and use the one that we calculated, yeah, negative 1,6 times 10 to the exponent, that to calculate the change in charge, to see if we can do that. So we know that if we're looking for number of electrons for this, then n will equal to the charge divided by the charge of an electron, and then that n will represent the number of electrons. Now the charge, remember I said it's going to be negative, so it's going to be what? Negative 1,6 times 10 to the exponent negative 19 coulomb. And then, so if I'm gonna use maybe the previous example, for instance, and then they're saying to you calculate the number of electrons transferred or removed from the charge. So I already have the final charge, and I need to use the first metal sphere. So if I'm gonna use the first metal sphere, then I'm gonna have to calculate the change in charge. So the change in charge is going to be the final charge minus the initial charge. So in terms of the final charge, I got negative 1,67 times 10 to the negative 11, and then now I must subtract something. So what am I going to subtract? I'm going to subtract the charge on sphere 2, so I mean sphere 1, which is negative 2, right, times 10 to the negative 11. And all of these, whenever we add them up, let me do the calculations. Let me try and do the calculations for you. So whenever I do the calculations, the charge then gives me what? 3.30 times 10 to the exponent negative 12. So now I have my change in charge, so I can be able to calculate the number of electrons. Remember I said to you, the number of electrons is equal to the charge over the charge of an electron, and the charge we have here is 3.30 times 10 to the negative 10. Is it 10? That's 12, sorry, to the negative 12 divided by the charge of an electron. So the charge of an electron, I'm gonna put 1,6, then multiplied by 10 to the negative 19, and then this will give me the number of electrons. So whenever I do my calculation, the number of electrons happens to be 2, 63, and then it's going to be what, times 10, and then to the exponent of positive 7 electrons. So this becomes the conclusion of quantization of charge in this case. So we also have what we call a neutral charge. What is a neutral charge? A neutral charge is an or a atom or material with equal number of protons and electrons. So it means this material will consist of equal number of protons and electrons. There will be inside the material. Let's use this one. As an example, inside this material, if we have 5 protons, then it will consist of 5 electrons. So then we say this specific object is neutral. It's neutral because this material consists of equal number of protons and electrons. So we have we know already that we have types of charges. So we have the positive charge, right? And then we also have the negative charge. So in most cases, we know the positive charge, we take it to be a proton, and then the negative charge is also taken to be an electron. And then we have a neutron, which is a neutral neutral object. So when we say that this object has got or is has got a lot of electrons, right, or this object is negatively charged, we mean that this object will consist of lot of negative charge, which is electrons. But whenever we say this object is positively charged, we mean that this object will consist of lot of protons or positive charges. So it means instead of having, for the positive charge, if we have the five protons, as we said, 1, 2, 3, 4, 5, it will no longer have 5 electrons, it will have 4 or 3 electrons. So there's an excess of 1 proton. So this object we say is positively charged. For this negatively charged object, we mean that if this object has about 3 protons, then this object will consist of about 4 electrons. And this object we say is negatively charged because of this excess of the electrons. So we know that charging involves the transfer of movement of electrons from one object to another. That's why we try and focus on those. And then we have what we call polarization or conduction of electrons. So polarization of charge changing by induction. So this here it has to do with what we call the aspect triboelectric charging. So in terms of polarization or triboelectric charging, what are we referring to? We are referring to inducing charges from a neutral metal or a substance or atom. So in this case, it means whenever we are doing triboelectric charging, then we will be considering the fact that these objects are not actually having any excess of positive and the negative charges. So then now we have to try and create either the excess of the proton or the positive charge or the excess of the negative charge, so that we can have somewhat the formation, or rather the introduction of Coulomb's law. So in terms of Coulomb's law of attraction, we talk about two things. We talk about attraction, and we also talk about repulsion. So in terms of attraction and repulsion, what we know about attraction is that unlike charges attract. So whenever we have unlike charges, they will always attract. But what we also know is that like charges repel. So whenever we have two like charges, then they will repel each other. So what do we mean, guys? This is what we mean. If you have sphere A or object A or atom A which is positively charged, then you have atom B which is positively charged, and you try to bring them close together, then these two objects, the force A on B will be like this, and then the force of B on A will force the object A to go in the opposite direction, and this will be the result, and this is what we call repulsion. So the same thing happens if we have two negative charges. So let's assume that A is negative, and then let's assume that B is also negative. So we are going to have a force that is going in the opposite direction of the movement of the object. So it's going to be force of A on B, in this case moving away from A, and then also you're going to have force of B on A that is moving also in its opposite direction. Then if we look at this, we conclude that it is still a repulsion. And then let us go to the third example. Let's assume we have sphere A which is positively charged, and then we have sphere B which is negatively charged. Then what we can take from this is that these two spheres will then have forces that are going towards each other. So force B on A will be going towards B. A will be going towards B, and then B will be going towards A. So these two forces are going towards each other, and then they will attract. So here we are talking about a beautiful woman, two beautiful women, or rather, let me put it this way: a woman and a man. So if you have, in most cases, two guys that are friends, then in this regard, there is no way these two guys can be in a relationship with each other, because they are like charges. Two women who are friends, like, chances of them being in a relationship are very low, not impossible but low. So we normally call that repulsion. And then this is, take the point where we have A as a positive and B as a negative, as a woman and a man, as you're looking at this girl down the street, and then she just attracts you, or you're attracted to her, and then in this case you both are attracted to each other. So this means that you guys will be drawn towards each other, and that's what I'm trying to get across. So in this regard, we can go to the Coulomb's law, and then the Coulomb's law, what we understand is that Coulomb's forces, the electrostatic force is one of the four fundamental forces of nature. So the others that we have what? Electromagnetic forces, we have weak and strong nuclear forces, and then we also have gravitational forces. So in this regard, the electromagnetic forces are a combination of what we have, electric and magnetic forces. So they act from a distance. And then, so if we look at these diagrams that we've been doing for A and B, we can see that the object exert equal forces on each other. So this is actually Newton's third law. And then also we have all four forces that we spoke about. Remember the four forces I said? We have electromagnetic force, and then we have what, weak and strong nuclear forces. All four of them we have are example of conservative forces. So the difference here is that the gravitational force is only an attractive force, but then the electrostatic force is both attractive and repulsive at the same time. So the definition in words, we understand that Coulomb's law states that the electrostatic force exerted by a one-point charge on another point charge is directly proportional to the product of the two charges and inversely proportional to the square of the distance. So this is what we actually mean. We mean that for every force is going to be directly proportional to Q1 multiplied by Q2, all divided by R squared. And then this is the mathematical representation. So in this case, when we say directly proportional, we mean that the force, whenever we have Q1 and Q2 that is increasing, the force will increase. But if we have the distance or the square, the distance increasing, then the square of that distance will cause the force to decrease, because we will have more of the distance between the spheres. So the force of attraction or repulsion will not be determined. So this is how we can try and represent it. So whenever we say the force is directly proportional to the product of the charge, we mean that if we have the so-called force versus the product of the spheres, then the total electrostatic force will be constantly increasing. And then so for whatever the increase there will be for the charges, the force will also increase. But here we are saying that if the electrostatic force is inversely proportional to the square of the distance, and what this means is that with an increasing distance there will be a decrease in the force, so that the force will then dip in this way. And then the other concept that we can go to or try and express in this case is that the Coulomb's law is actually similar to the Newton's law of universal gravitation. So how are they similar, or the similarities and the differences? They're similar because they're talking about the product of the quantities and then inversely proportional to the square of the distance. So the differences there we have is going to be the Coulomb constant, and then also the gravitational constant. And then the other thing with regards to Coulomb, we have attraction and repulsion. And then whenever we talk of the universal gravitation law, we're talking just only on attraction. And then also Newton looks at masses of object, whilst your Coulomb's law looks at charges. And then Newton just focuses on attraction, like I said. And I think we can wrap it up there. And then in the next part we're gonna be doing calculations on the electrostatic force, the electric field, and we will also be doing some some exercises which are exam based exercises for grade 12s. To those, thank you for now.